Good evening, and this is going to be our chapters 9 and 10 lessons, and these are all about remote sensing. So when we talk about remote sensing, what we're really talking about is our ability to acquire spatial information from a distance. So some of the earliest examples of remote sensing are basically just aerial photography. This example here we have is an aerial photo taken of Boston in 1860 by James Black, and it's the earliest surviving aerial photo taken from a balloon in the US. And so this is just one example of how we can gather spatial information about the configuration of locations historically. But photographs from other aircrafts and things like that date back even a little further than this, back into the late 1850s. There were a couple people over in France that sort of pioneered this, and then of course by the time World War I rolled around, we were using this a great deal, particularly after the advent of modern flight, following the groundbreaking works of Orville and Wilbur Wright down in Kitty Hawk. So here's another example. This is San Francisco, and this is titled In Ruins, and this is from an aerial photo in 1906 by George Lawrence. And this was a suspended and remotely operated camera that was hooked up to a bunch of kites, 17 kites specifically. And this is basically 1,000 feet over San Francisco Bay, looking at what was left of the city after the Great Earthquake. There are other examples and other ways that we can use this. One example here, we have a photo from World War I that shows us where the earliest documentation of the trenches were and how that related to what was going on, where we would use literally aerial photos to figure out, where we're going to attack or not. And so this sort of thing evolved a great deal over time, and eventually we would use this to identify all kinds of interesting places and things that we needed to consider as targets. For example, World War II, we figured out where they were building the V-2 rockets, and later went on to sort of try to bomb the tar out of it. We developed airplanes that were made specifically to fly higher than what anti-aircraft fire could travel and faster than other aircraft, so that we could go and take photos wherever we want. This specifically was the U-2, traveled over 400 miles an hour at over 70,000 feet, and it worked great right up to the point that the Soviets could travel as high and go as fast, and then they shot one down, and that sort of got us to where we migrated to next, which was satellite photos. So let's look at some more stuff. So here is a photo that has quite a lot of historical significance. This is aerial imagery of Cuba, and this shows the missile facilities. This was shot during the Cuban Missile Crisis in 1962. I believe this is probably taken with a spy plane, not a satellite. But anyway, they used this aerial photo, this remotely sensed data, to determine that they were in fact building missile silos and sites in Cuba, and led to the standoff, the blockade, and ultimately nearly started a world war, but cooler heads prevailed, and we got back to where we needed to be as far as having a fragile peace. This is the U-2 spy plane. Now, some of you who read a lot of Marvel comic books are familiar with the version of the Blackbird that the X-Men piloted, but in reality this was a highly classified covert piece of avionics that the U.S. government developed specifically for flying very high altitudes and taking pictures. The U-2 was the first. This is not actually the U-2. This is a different one. What is this called? The SR-71. And so it was sort of a later version. The U-2 had a really long wingspan and looked slightly different. Anyway, we eventually moved on from sending up planes like this and began using more unmanned aircraft. And the unmanned aircraft allowed us to go in and get higher quality imageries from lower elevations and dangerous locations without putting pilots' lives at risk. So here's an example of one of those drones that we popularized and developed over the years. The use and ability and capacity of these particular devices has increased tremendously, from initially just taking pictures to then adding the ability to carry a payload, bombs and that sort of stuff, to now even automatic weapons, to make it quite a interactive platform that is capable of doing much more than just collecting surveillance information, but actually providing leverage or fire, if you will, on a target. But not all drones are the size of these large anti-aircrafts. There's also small drones, much like you would have at home, that can provide localized intel or locally captured remote sensed information, or simply are something fun to fly. It literally just depends on what you're trying to do with it. So I want to talk a bit about how this actually works. When we talk about photos, the first thing is whether we're taking just a regular picture or if we're taking something else. And so when we look at the natural sort of colors that we see black and blue and green and red, but the actual wavelengths that we look at could be quite different. And so this example here shows you what a false color infrared would look like, where we take our blue, green, and reds and we shift those and include a near infrared, and actually from all of this we get to the point where we can not just have a color image, but we can have some of this other information there that allows us to do a lot. And by a lot I mean identify things that you couldn't see with the naked eye or identify in a regular color picture. So here is a photo, and clearly looking at this now, most of the Midwest or wherever you take a picture like this is not going to be red. Why is this red? This is a color infrared or false color infrared, depending on what you want to call it. And basically what happens in a situation like this is the visible colors are now identified with the improper spectrum related to that color. So the blue in the image is now black. The or well, no, that's not exactly right. You can think back to the previous slide. Basically what we're doing is anything that's black in this one should be blue, anything that's blue in this one should be green, anything that's green in this one should be red, anything that's red in this one should be in the near infrared. And the near infrared is interesting because it absorbs things quite differently than what the regular spectrum would, and so it is more associated with heat, and it's also associated with how and what it absorbs, so it allows you to differentiate between different vegetation, and also allows you to differentiate between not just the vegetation but objects that are trying to pretend to be vegetation. When we take these photos from above, some of the things that we need to realize is when you're looking down, there's only one spot where that picture is literally framed up and focused directly beneath you, and that spot looking right down through the middle of the lens is called the principal point. And as you move away from that in all directions, you'll see the images appear as if they lean outward, and that effect is called relief displacement, and that is something that we actually utilize quite a lot. This is a sort of a three-quarter perspective where we're looking at something off in the distance to do this, and when we have an image like this, we look at it from the side, we get this oblique angle, and it's positioned so that we can see different things. But I just want to kind of recap a little bit quickly. So we had that principal point we talked about earlier, and how relief displacement occurs. Now when you get some photos it looks like everything is perfectly looking straight down from above. That is an orthophoto. An orthophoto is one that's went through a process called orthorectification, and basically what that means is they've taken out that lean by taking different data sets and combining them together. And then another thing that we want to talk about here a little bit is some of these other programs like NAIP, which is a program, it's NAIP, that the U.S. Department of Agriculture put together to collect high quality aerial photos across the country for various purposes in terms of agricultural uses. So now that we've got some images and we can do some things with it, how do we utilize it? How do we make some sense of something like this, where we see just this image and we see this tower and we see this shadow? What can you actually learn from something like this? Well, it turns out you can learn quite a lot. First thing is you can just visually interpret the image, which is really the process of identifying objects and features and that kind of stuff. And so you say, yeah, this is a building, that's a parking lot, this is a road, etc. There's a lot from that. And how can you do that? You can look at things like patterns. Look at the way things are arranged and try to determine, oh yeah, these are buildings, or these are fields, or these are what have you. We also do a lot of sight and association, and this would be things like large, slightly darkened areas next to buildings being a strong likelihood of being a parking lot, for example. We can also look at the size of objects and try to make out some sense of what they might be based on that. We can look at the shadow and how the shadow is cast from these various things, and from that we can also learn quite a bit about how tall things are. We can also learn about the shapes of things as well, because some things have unique and distinct shapes, like the Space Needle in Seattle. And we can also look at the textures and the tones in terms of the colors and that kind of stuff, and try to figure out what we think things are. All these sort of ideas are quite useful, but the one that probably does the most for us, I think, is likely photogrammetry, which is the process of obtaining measurements of things from aerial photos. So here we have a Space Needle in Seattle, and if we know a certain amount of things, we can get some idea of the size of stuff. And really, it's not any more complicated than doing high school trigonometry. So when you look at something, whether it's the Great Pyramids, and you see the shadows and how it's cast, if you know the angle that you are looking at, and you measure the displacement of the image relative to that, you can figure out how tall something is. You can also do it by calculating just from those distances. So there's an equation in the textbook and goes through it. And I'm not going to spend a whole lot going over how you actually go about calculating it, but it's really just, it's simple trigonometry to figure out how tall something is based on the length of a shadow and an angle of the sun and all that kind of stuff, and it works really remarkably well. And it goes a little something like this. The angle of the sun, where it's at from your spatial position. If you can measure the length of the shadow and the angle, then you can figure out the height. Opposite, which is h, over adjacent, which is L, is the tangent of that angle, and if you know what that angle is, you can then figure out the hypotenuse, which is the length of the shadow in 3D. But what you're really interested in is h, or the height, and so opposite over adjacent, if you know that angle, you rearrange the equation, and voila, there you go. You know how tall something is. They do a lot of this work remotely. Government agencies spend a lot of time figuring out what these things are, and ultimately trying to make use of this information for any number of purposes. Alright, moving on, let's take a look at Chapter 10. So Chapter 10 is all about how we actually use remote sensing and how these things sort of work, and so we're going to talk more about that. So you have some source of energy, or the incident energy, like sunlight, comes down, hits the surface of the Earth. Some of it is reflected away. Some is absorbed in the atmosphere, some is absorbed by the object that it hits. So there's some degree of this energy balance that goes in different places. Remote sensing satellites have spectrophotometers that allow it to collect this information and measure what is being reflected. We also know what is being transmitted, and from the differences in that we can sort of piece together what is where. And here's the interesting thing. Just a little bit about light and wavelengths. Remember, the wavelength is the distance between the tops and the peaks, and the frequency is the number of peaks per unit of time or distance. Ultimately, we use this to characterize the particular energy we're looking at. And what we're really talking about is visible light. And so across the entire electromagnetic spectrum, which goes from all the way down to tiniest of gamma rays to all the way up to the longest of radio waves, in between there's a very thin section between 0.4 and 0.7 micrometers that we can actually see, and that is called the visible range. And so if we looked at that, here's another way of looking at it in terms of how much of the energy is transmitted through the atmosphere. And you can see when you get to the really small frequency stuff, there's not much of it that's transmitted. It's mostly absorbed by ozone and oxygen and other things. And then as you approach the visible spectrum, that numbers we were looking at earlier, 0.4 to 0.7, you see that during this range, the yellow or the orange color goes much higher, and nearly all of the energy goes through the atmosphere without any difficulty. But then once you get above the red, you start seeing less of it being transmitted, and you also get a couple little peaks here, and these peaks are where water absorbs part of the infrared. And as you go on up through, there are other areas of transmission and absorption associated with different compounds, all the way through up into the microwave. So what this does is it creates this unique environment where different things absorb or reflect different frequencies of energy and different amounts. And so here we have a graph showing the wavelength across the bottom, and across the other axis we have the percent reflectance. So this is how much of the total energy that was put on a surface is reflected, and then across the bottom it's at each wavelength. So for example, then if we looked at the grasslands, which is the light green line, you see that it starts out relatively low in the blue end of the spectrum, and as we move more towards the red and the visible, it increases and drops back down. Then we get to 0.7, and then we get this huge spike, followed by a couple little dips as we move on out. Move from the grassland to the red sand pit, you can see that the color goes up much further as we approach 0.6, which is more towards red, which is what you would expect, and has a very different behavior moving on across. Piney woods would be very similar to grasslands, but they have a lower percent reflectance in the near infrared. That could be useful. Then we have silty water, which is basically just water that has a certain amount of sediment stirred up in the column, and you can see how it goes up to some point and then drops down and sort of carries on across the bottom, all having very different signatures. But you have to know where to look. For example, if you're trying to identify the red sand pits, around 0.6 would be the easy spot because it should be very bright. If you're trying to differentiate between grasslands and the piney woods, you want to get up in the near infrared, things above 0.7, because at that point the reflectance should be much higher in the grasslands than they are in the piney woods, and the water should be much lower than any of them. And so that's sort of where we're at with those. So here's what we're talking about. Light comes down, light bounces off, some is visible, some is not. And what they're looking at here in figure 10.6 is one of these ways we can sort of go about collecting this information, to think of other ways that we can label it, learn from it, categorize it, make some use of it. And so what we're talking about here is going to be something relatively simple called the NDVI, which is the Normalized Difference Vegetation Index. And what the NVDI does is it allows us to look at the amount of visible and infrared light and how those two change between one another. And by simply doing these equations where you look at how that works, where you take the near infrared minus the red divided by the near infrared plus the red, you get a percentage or a number, and that allows you to characterize the data very differently. And what really helps is it allows you to go from one image to the next where other things could have been causing problems, and so it may have depressed the overall amount of energy. It doesn't matter because we're looking at the ratio of one to another as opposed to the total volumes. So this is just some of the things that we can use. There are other types of stuff we could look at. These different bands we've talked about to some extent. We've talked about the transmission and absorption. I want to go back and just talk for a little bit quickly about what actually happens in the atmosphere before the light gets down to things like these trees. We have these windows where we have a high transmission, but in other places it doesn't work quite that way. And that's because we have scattering. We have things like Rayleigh scattering and Mie scattering and non-selective scattering. Rayleigh scattering has to do with these significantly smaller parts than the wavelength of the light, and it causes some interference. And then there's Mie scattering, and it's just when we hit particles that are roughly the same size as the diameter of the wavelength. And then we have non-selective, which is when we hit anything that's really bigger. And they all behave very differently, but it's important to kind of get an idea of what some of these things are. So look at your textbook. There's these wonderful little green boxes that give you things like atmospheric window and Rayleigh scattering. It tells you more about it. Read up on them. There'll probably be test questions. Okay, so we've talked about that, and we're talking now more about the spectral signature. Let's move on to the next. Alright, so the NVDI, I was already talking about that a bit, and if we look at it, what it does is it allows us to see healthy vegetation. If vegetation is healthy and green, it will look differently than if it's dying and brown. And that can come in really helpful. For example, if you look at a map of Africa and you look at the vegetation index, you can get some idea. The higher the number, the greener the vegetation, and the less green the vegetation, the more arid the region. And so you can literally see where the Sahara comes into play. So how do we view a lot of this stuff? Well, it depends on what we're looking at, but in general, this information comes in rasters, and then for the rasters, for every cell, we get this DN number, or this brightness value, depends on what you want to call it, and it's really just a measurement or a number in that particular location. And depending on the data type, we'll adjust what we can have. So you might have 8-bit, or you could have 16-bit, or you can have 32-bit, and these all changes the numbers that you can have. The most common setup is this 0 to 255 scale, or the grayscale, which is typical of an 8-bit image, and from that things get assigned something more on the bright to dark relative to those values. The other thing we can look at is colors and what they actually mean. There's a couple of different ways we can look at colors, whether we look at a composite, additive or subtractive models. I'm not going to go into too much in that. I'm not going to spend a great amount of time going over that, but in general, with remote sensing data, we either have a single panchromatic image, or we have a multi-band raster where we have a band for each of the red, green, and blue colors that then go together to form the colors we need. So here are some of the different 8-bit combinations of red, greens, and blues, and you can see that if you have all red and all green but no blue, you get yellow, etc. And you go down the list and you can kind of get some idea of how the combinations lead to the different colors. Now, where does this data come from? Sometimes we get it from satellites. In satellites, you might have things like band 7, band 4, and band 2, and they're all in grayscale, and then from that you can pull out these different things and set up these different combinations. An example here in step 3, we're looking at 742, which is a unique band combination that is designed to allow you to see certain things. And there's multiple of these, but we can look at true color, false color, and standard false colors, and there's other things. You can look in your textbook to get some idea of the difference of these. Again, green boxes. True color is an image arranged by placing the red band in the red color, the green, and the blue in the blue. False color basically happens when we place the red, when the distribution of bands differ from placing the ones in their appropriate ones. And standard false color is when we place the near infrared in the red goes in the green goes in the blue, and the blue we just sort of forget about. And some more combinations. Here's what that kind of looks like when it plays out. If we look at an image and we put it in a false color infrared, what would look like A would look like B. Here we have 3 different maps, and This shows us something that's important. This looks at change over time, 87, 91, 2000, 2010, and you can see how the growth and development has occurred in the area as it's expanded. Some of the stuff you can look at with your various tools, looking at different things that you can do relative to some of these things. You can go in, and this shows you how to do it with, I believe it was, well, let me think here for a second. I can't remember if this was in, what is this? No, this is using Multispec, which is just one of the free softwares that are out there to sort of look at this. We'll do this in much more elaborate detail as you further through your GIS career, but this just shows you how you can go in and set some of these different channels, figure out what you want, and adjust the colors. And ultimately you can then look at how the data is distributed. You can see where things go. You can zoom in and look for tiny differences. You can graphically look at how the values shift. So when it's all said and done, there's just so much you can do with remote sensing that's really incredible. Whether you're looking at taking LiDAR information and using it to map a surface, or some satellite information that you're then using to map where we see healthy vegetation or changes in vegetation or changes over time, or using aerial photos to identify where missile bases are being built, or what's going on, and any number of things like that. There's always a lot of opportunity to do that. We can also measure the size and shape of things and orientation and figure out where stuff is from aerial photos. We can go back and take historic photos and use those to do any number of things. We can collect information from small, simple, personal level drones to complicated flying unmanned aircraft, all the way up to secret spy planes and space satellites, and any number of ways that we can do this. So there's a ton of sources of remote sensing information that are out there. It can get complicated making good use of it. In fact, it's literally a class all by itself here at NOVA, and in all likelihood, in all honesty, it's a field of study where you can devote an entire academic career to mastering its individual skills and literally become proficient at just that. So don't mistake what seems to be the simplicity of remote sensing for simplicity, because it's not. It's a simple concept in that we collect information from afar, but how we collect it and what we do with it is anything but simple. Thank you. Bye.